It started, when she was really young, around 3, and every time she'd look into the mirror, she would see herself, but she made it her friend, and she named it Tori.
Well, Tori's my best friend. People think it's a little weird, but I think she's just wonderful. I mean, we have the same style. We almost wear the same thing every day. We have our rough patches, but we usually work it out. We have really similar forms of communication. We talk to each other, and she's just a really cool girl.
Lori Fisher suffers from a rare disorder, also known as reflective confusion. There is no second girl behind the mirror, but instead, an illusion is created by simple motion of electrons. Light rays coming from the source travel through air in all directions, and some hit the electrons on the surface of the mirror. These rays are created by the vibration of magnetic and electric fields. When those fields meet the electrons on the mirror's surface, the mirror's electrons move more energetically, and then the energized electrons re-emit light back into the atmosphere. We can figure out where light will travel by keeping in mind that light always travels along a path between the source and the boundary that takes the shortest time. The angle at which a ray of light can enter hit the mirror is called the angle of incidence. One can measure this angle with respect to the normal, an imaginary perpendicular line to the surface of the mirror. Light reflects back into the atmosphere at an angle. This angle is equal to the measure of the angle of incidence, but is in opposite direction with respect to the normal. When light reflects off the surface of the mirror, light rays diverge in many different directions. Some rays hit the eye, and that's how we can see an image. What Lori thinks she's seeing is a figure behind the mirror, but only because light reflected from the mirror enters the eye the same way it would as if a person or object were actually in that spot behind the mirror. The image is an illusion called a virtual image, and not Lori Fisher's best friend. Divergent light rays seem to be coming from a specific point behind the mirror. It is at this imaginary point where Lori's imaginary friend lives.
I just want my little girl back. Hello, boys and girls, and welcome to Physics with Phyllis. Today we're going to be talking about refraction and mirages. Ooh! Oi, who's this? It looks like my good friend Fievel. Let's see what he's doing. It looks like he's headed for the railroad tracks. Let's follow him, shall we? Silly Fievel, he thought he saw his parents, but it was only a mirage. Come with me and I'll show you how mirage is really made. Let's go! Oh, hello! Didn't see you there. Well, oh yes, right, mirages. Okay, so this is a light ray, and say that this light ray wants to get from this purple dot to this pink dot, and light always wants to travel in the fastest path possible. That's Fermat's principle. So, in order to get there as fast as possible, which way would you think it would travel? Was that in a straight line? That's what I used to think. But in this case, it's different. What happens is, here at the ground level, the air towards the ground is much warmer than the air up here. And light travels much, much faster in warmer air. So instead of going along this way, slow, mosey, 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 all the way to the pink dot, it wants to take a little shortcut. So travel goes down here into the warm air and zooms over to the other side where it can reach the pink dot much faster.
Today we're going to talk about refraction of light. So one day, so in refraction, there's this thing called Snell's law. There's this guy, William Brothers Snellius, and hold on. In the 16th century, one day in his house in Dutch, he was drinking water and he was like, hey, wow, this straw looks different. And it looks funky. It's like looking funky. Dolius knew that when you put, it's two different mediums and it's changing in speed, like, pew! Oopsie, sorry. Okay, so anyway, Snell saw, sorry, I'm a little drunk. Snell saw that the angle that the straw went in the water made it look bigger. And this is a manifestation. That's a hard word. He's manifestation of refraction and of light traveling from moving faster in the air and slower in the water. And the straw looked bigger and closer to the water than it actually is. And it's actually refracting toward the normal. Basically, refraction is a light in the air, but it's going to the water, but it's moved slower in the water. Like that. Watch. See my straw? Between here and water looks different. Now it's bigger. Small.
This is Blorp, Mr. and Mrs.
One-day T-blobs wäre Walken along in T-Park studying and observing Fahrtheater.
Oh, look at the spectrum of color. I believe Earthlings call it a rainbow.
A rainbow? But where did it come from?
Rays of light from the sun hit droplets of rain on contact. The light disperses and refracts, or bends. The light also continues to reflect off the back of the raindrop, and then back out of the drop and toward the atmosphere. Upon exiting, light refracts a second time, bending the light ray and changing its wavelength. This is why the rainbow's many colors are in that order you see. Red light has great wavelength, it deviates the least, while violet has short wavelength and deviates the most of all. The other colors fall in between, from greatest wavelength to least in order of colors in rainbow.
Now I understand. Your great capacity for knowledge impresses me. As the Earthlings say it. Would you be my wife?
I would love to accept this luminescent stone of such great internal reflection. Let us walk off into the dropping light source of Earth.